So here's the outline of the talk. So first, we'll give a brief introduction of the topic, image geolocalization. Then I will focus on three of our recent papers on cross-view image geolocalization. Then finally, I will give some of the future directions on this topic. Okay. So what is image geolocalization, right? So given an input image, so this can be a query image that collected maybe from internet, and we want to know what's the location of this place, right? So the output is a GPS coordinate, indicating the longitude and latitude of the place, presented in this image. So to do this image geolocalization, we want to create a reference database. So for this reference database, it could be from the same view. Let's say the query image is from the street view, and the reference database can be collected from the same view, that is from street view images. And these images are all geo-tagged, so which means each of the image will have a GPS tag. So what we do then is to find a best match based on this reference database. Let's say we find the best match is this image, then we can using the GPS coordinate as the prediction for this query image. Okay. We can also build this reference database from another view. Okay, not necessarily from the same street view, but we can also collect the reference image in the, for example, area view or satellite view. Okay, so and all these area view images are also geo tagged. Okay, so the procedure is going to be the same. So we find the best match, and we're using the GPS tag as the prediction for the query image. So the question is, how do we define similarity, right? So the typical way we do is we learn the similarity, via metric learning. So basically, if you have a query image, it will go through a deep learning model. It will generate a feature embedding. So in this embedding space, maybe this feature vector appear here. And you also, in the reference database, you will have, positive images corresponding to the query. Okay, you also have a lot of negative images correspond to the query. So they all go through the model and generate the feature embedding. So basically, this will create a triplet, right? You have a query, we consider as an anchor. You also have a positive image and also negative images. So in this embedding space, we want this positive pair, right? So this green one to be very close to the query, okay? At the same time, we want the negative images to be far away from this query. So image geolocalization are very important for various real-world applications. For example, we can use it for automotive applications. So maybe the phone GPS you have is very noisy, right? So it's not very accurate. We can using image geolocalization method to kind of calibrate or refine the GPS location for navigation. We can also using, directly using the image geolocalization for street navigation. And we can also using geolocalization for UAV pose estimation or help the UAV to navigate in some of the GPS denied region, right? Because some of the regions are very restricted. You cannot using any of the GPS signal. Then you can only rely on this kind of visual information to guide through the navigation. So as we mentioned before, so for this image geolocalization, to build a reference database, we can either collect the same view, right? If the query is street view, we can collect the reference database from the same street view, but we can also collect images from a different view, like satellite images. And for the same view geolocalization, because only a small number of cities in the world are covered by this dense ground level imagery. But on the other hand, for the satellite images, there is a more complete coverage, of the Earth. So that's why in this talk, we'll focus on cross-view image geolocalization. So the first work is we majorly discuss the issue of orientation alignment in image geolocalization. So this is the work published in WCB 2021 with my student CJ and Tao. So the recent cross-view image geolocalization method is able to achieve high, accuracy, but the high accuracy actually depends on several assumptions. So one assumption is the orientation alignment. So that is to say the training and testing data set, so the images are well aligned in terms of orientation. So take this as an example. So this is the street view panorama image, and this is the reference satellite image. So the orientation has been aligned. So that means if you look at the yellow bar in the street view and also here in the satellite view, they all have the same alignment information. So this indicates the south, and on the very left beginning indicating this is the south. Okay. So, but in real world applications, images may not be geometrically aligned, right? Maybe I have a reference database is not aligned in this way, south pointing to this direction, or maybe I have a street view image can be shifted a couple of degrees, maybe to the right or other directions. So this motivates us to answer the following questions, right? So how would the alignment information affect the retrieval model in terms of performance? And without assuming the images pairs are aligned, how to effectively improve the retrieval performance? And finally, is it possible to estimate alignment information when there's no explicit supervision? Okay. So let's first look at the first problem, right? So how the alignment information would affect the retrieval model. So we studied this question by empirically did some experiments. So we take the commonly used benchmark called the CVUSA dataset. So in this dataset, the orientation alignment are fixed. So as I indicated here, so this always indicating the south, the beginning, and this direction indicating the south for the aerial image. So if we're using this aligned orientation aligned image to train the retrieval model or image matching model, and we also test the model on the aligned the test set, and we can see that a simple baseline is able to achieve 60% of top one record accuracy. Okay, but if we train the model using the aligned image pair, but during the testing or validation, we randomly rotate the aerial image, okay, as shown here, right? In this example, I rotate clockwise 30 degrees. And if we randomly rotate images for all the validation images to destroy this kind of alignment information, you can see that the performance drops significantly, right? From 60% to only 13.5%. So there's a dramatic drop in terms of retrieval performance. And this is intuitively makes sense, right? So the geometric, alignment information provides a strong cue for this image matching. And if we destroy that, the performance will be dropped. So that leads to our second question. So without assuming the image pair are aligned, right? So how do we effectively improve the retrieval performance in this kind of more realistic scenario? So we approach this problem from the metric learning perspective. So because these metric learning techniques are independent of this kind of alignment assumption. So here is the typical framework to build this image retrieval or image matching pipeline. So the input will be the street view image, the query image, and the reference image, which is from the area view, since we are considering the cross-view geolocalization. So for some of the data set, the street view query can be a panorama image, but for some of the data set can be a cropped, a limited field of view, just like a partial view of the street view. So either way, we'll send these two images to this two separate CM model, right? So one is to encode the feature from the street view, and the other CM model is used to encode the feature from the area view. And we generate a feature embedding, and we hope to design some of the matching laws. Hopefully that similarity, we can learn very good similarity measure. So there are a couple of very commonly used matching loss in this retrieval paradigm. So one is the triplet loss function. And it's so the formulation is here. And this DIP indicating the distance between the anchor and its positive. So the anchor is considered the query, and this DIN is indicating the distance of the negative sample and the query. Okay, so the idea is that we want the distance of this positive pair to be much smaller as compared to the distance of the positive pair, right? So so if you look at the loss function, right? So if the dp plus a positive margin f is still not greater than the distance of the negative sample, then we don't incur a loss. But if it's not less than the negative distance, we're gonna incur a loss because the feature you learn may be not good enough, right? So the positive pair, the distance is not very small. So we'd have to penalize these kind of examples and able to learn better feature representation. So there's also some improvement based on the triplet loss function. So for example, this weighted soft margin loss. And later we get inspired by this binomial deviance loss, which is used for person re-identification. And basically, this has two separate terms for the positive sample and the negative sample. And based on this binomial deviance loss, we made some modification. So basically, we assign different weights for these positive samples and different weights for the negative sample. Also, we have assigned different margins for positive sample and negative sample. Okay, so this gives the model more flexibility based on the negative and positive samples. At the same time, as in the cross-view geolocalization, we only have one positive match, right? So for a query, we only have one positive match. Has the same GPS location, right? Other images have different GPS locations were considered negative samples. So we have a lot of negative samples. So it will be much easier, we pull the only matched sample close rather than push all the negative samples away. So this can be achieved by assigning a much smaller value to alpha p than alpha n. So I'm not going to dive into the details behind the rationale of this, but we have some detailed analysis in the paper, so you can refer to that. So we did some experiment on these two benchmark data set. One is CVUSA, the other is the VO data set. So if you look at the top one recall accuracy, right? So that, recall at K means if the ground truth reference image appear in the top K retrieved image, it is considered as a correct. Okay, so the top one means we only retrieve one image, and that should be like the ground truth image if we want to consider that's a correct retrieval. So if you look at the top one recall, our method is able to outperform other existing method considerably, right? So as compared to this paper, we are able to achieve almost 6%. Okay. One thing to note that all these methods do not assuming this kind of orientation alignment information. So that's why we want to compare with them to make a fair comparison. And we also study the effect of the alignment information. So in the experiment, so we have these two settings. One is with the alignment. The other is without alignment information. So without alignment means we randomly rotate the aerial images in the training and the test set to destroy that alignment information. So as you can see from the result that the proposed method or the loss is able to consistently improve the baseline, which is just using the normal soft margin loss by a considerable margin. Okay. And here we show some of the visual examples for the geolocalization result. Okay, so on the first row, it shows the query street view panorama image. And the second row, it shows the top 5 retrieved image. Okay, so the green indicating the ground truth, actually, that's exactly we are able to retrieve as the top one. Okay. And this is another example. Here, this is from another data set, VO data set, which you only have 90-degree field of view, not instead of panorama. So for this example, we are also able to, get the top one correct as the ground truth. And here is a failure example. The top one, although the similarity has the highest similarity measured at 0.78, but it's not the ground truth, the correct one. So the actual ground truth is actually ranked 5,984 in our retrieved list. So this is a failure case. But if you look at the image, it's a very difficult one. So the visual information from the query is very limited, right? You only have like this road. It can be any type of road if you look at the retrieved satellite image. And we also did some visual explanation of the matching result using a technique called grading cam. So the grading cam stands for gradient weighted class activation map. So basically, this is commonly used for, do some explanation for your deep learning model for the classification, right? So if I have a classification model and make a decision as this is a cat, the grading cam is able to highlight, which pixel contribute the most to the decision of a cat, right? If I make a decision of a dog, and you can see that the grading cam, the heat map kind of change the focus, right? They highlight the region of a dog, okay? So this indicating where the pixels contribute the most to the decision. So we adapt this technique in this metric learning framework, and we want to show that, from these, the query and the retrieved reference image, how they contribute, which region contribute the most to the similarity measure, right? Let's say I have this retrieved area image has the similarity of 0.9 as compared to the query, right? I want to see where are the locations or regions contribute the most to that similarity measure, 0.9, okay? And we show a couple of examples here. So this is the query street view, and this is the retrieved area view image. And this is how grading cam is able to highlight some of the region contribute most to the similarity measure. So that leads to our last question, right? So is it possible to estimate the alignment information when there's no explicit supervision, right? So we get some inspiration from the grading cam visualization. That is, let's assuming there's no alignment information, right? We can randomly rotate the satellite image into different degrees. So in this example, we have 25-degree and minus 34-degree rotation, and we conduct this grading cam visualization, and we find out that the heat map provided by the grading cam doesn't change too much, no matter the degree the rotation is, right? So from these kind of activation map. So that means the grading cam activation map actually has some rotation invariant property. And we want to leverage that to estimate the rotation angle, okay? And this is how we do that. So once we have the grading cam activation, and we can do some thresholding and generate this kind of binary mask. So this binary mask mostly highlight the most activated region, okay, on the area view image and the query view image, okay. Because this is the matched pair, right? So the highly active region most likely related to the object, related to the same object, right? Maybe the road, the same road, or the same building, okay. And if the image pair is well aligned, right, the angle distribution of the activated pixel from the two views should be similar. Okay, if they are aligned, their distribution should be similar. But in this case, we are rotating for some certain angle. Then if we look at the angle distribution, we are able to do this kind of cross correlation and find the shifted angle so that these P aerial and the P street can best match to each other, okay? And we're using this method to do the orientation estimation. So it's actually give us a very good result. So for this example, we are rotating 126 degrees of the area view image. And based on that method, we are able to estimate the rotation angle of 125.2 degrees, so which is very close. And we also did some qualitative measurement on the whole data set, and we provide that result in the paper. Okay, so in summary, from this work, we found out that the orientation alignment has a great impact on the retrieval performance, and this point is overlooked by the prior work. And we show that the improvements on metric learning techniques is able to boost the retrieval performance. And we also discovered that the orientation information between the cross-view image can be estimated when the alignment information is unknown. Okay. In our follow-up journal paper, we did more on this kind of visual explanation, and we make it more general, not just for geolocalization, but in general for deep metric learning, like image retrieval, personal real ID, face verification. So if you're interested, you can check our transaction paper here. Okay, so the second work, we are studying the issue of spatial alignment in the image geolocalization. And this work is published in CVPR 2021. And we named this method and the data set called Vigor. Okay. So here we come to study the second issue in this field. So existing works simply assuming that each query ground view image has only one corresponding reference area view, whose center is exactly aligned at the location of the query image. Okay, so basically you have a query image, I have a reference image, and the query is exactly located at the center of the reference image. So that's the assumption of the prior work for this cross-view image geolocalization. And all those kind of data set used are designed in this way. But this is not practical for real-world application, right? Because the query image can be generated at arbitrary location in an area of interest. And the reference image should be captured before any query emerge. So here is an example to demonstrate this problem. Okay, so we have a reference image here, which is from satellite view. So the query may not occur like right in the center of this reference, right? So for this red star, which actually shift a little bit over the right, so that's this query corresponding to this location. Okay. I can also have another query, okay, which is this green star, which is appear here, is again not the center of this reference image. So to study this problem, because as I mentioned, the existing data set, they all designed or collect the data, assuming the center is the query location. So to study this problem, we create a new data set. So to generate this data set, given an area of interest, for example, you have maybe a city of Chicago, okay, a certain area of interest, and the reference area image are densely sampled to achieve a seamless coverage of this area interest. And then the street queries can be captured at an arbitrary location, okay? So by dense sampling, we mean we do so by do this kind of overlap sampling. Okay, so you have a area image located here, then we have some certain ratio of overlap and generate the second or sample another area image so that any arbitrary query emerge, there's gonna be some of the reference area image is able to cover that. Okay. And because of this dense sampling strategy of the data set, and our setting is go beyond this one-to-one correspondence, right? So for example, if we have a green star in query location here, you may have sampled an area image, which is located exactly at the center of this query location, right? Indicating by this green box. And we did indicate it as aligned, spatially aligned. But you may also have a reference image, which is sampled at this red box, red square here, a little bit shift. And you may also have another one, which is this blue box, right? This query location appear at the edge of this sampled area reference. So we define these different type of reference image as positive and a semi-positive. Okay, so for the positive reference, we define as the query location is within this kind of inner square. Okay, let's say the reference image has a length of L, the square, and if the query location is within this inner square, we consider this is a positive. Okay, so for this semi-positive, the query location is going to be outside the inner square, but still, right? So for the semi-positive, it provides some of the partial information related to the query location. And we generate this data set by sampling 4 major cities in the US. So one is the Manhattan area in New York, and the second Chicago, third is San Francisco, and the last one is Seattle. And this is a comparison of our data set with the existing ones. So basically, our setting is more realistic. The query location can be arbitrary, not center aligned. And also, each of the queries, we have multiple reference, not just one-to-one matching. Okay, then the problem becomes more complicated. So to do this geolocalization in our more challenging setting, we resort to this cross-to-find cross-view localization pipeline. So basically, this is the same input as before, right? So you have a street view query, you also have an area view reference, and they will go through these 2 separate CNN network to do the feature encoding. And this is just a one feature enhancement block we are using to improve the feature representation capability. And you also have the common metric learning loss, right? So for example, the triple loss. But at the same time, we add a side branch. We add another branch that is to do offset prediction. So once you have the retrieved top-on image, we want to refine the prediction, because now the GPS coordinate or the query location is not located at the center of the reference, right? It has some offset. So we want to predict that offset. So that's why we add another branch, which using just a couple of MLP layers. And also in our setting, we are not only have one reference image for one query, right? So we also have other reference, especially these semi-positive images, right? So in this case, how can we make use of these semi-positive images? So one simple and direct way to use them is consider these semi-positive as positive example, right? And just using that and to do the to train the model. But if you look at the result here, which is the second row, right? If we consider these semi-positive as positive, and the performance actually dropped, as compared to if we don't consider the semi-positive examples. This is because the semi-positive, although share some of the partial information of the query, but it also introduce some novel information which is not related to the query. If you force them consider the positive, it will confuse the model, right? It will learn something that make the model confused. So that's why you see the performance dropped a bit. So we propose a method to take care of this problem. That is, we force the ratio of the similarity in the embedding space to be close to the ratio of the intersection of union. So basically, we're using the intersection of union to weight the similarity, right, accordingly, not just blindly to make it treat it as a positive, but we weight them based on the IOU ratio. As you can see there, the performance is able to improve as compared to we are not using these semi-positive references. So after the image retrieval, as I mentioned in the overall pipeline, we also have a branch to do the offset prediction, right? So basically, what this does is that once you have this retrieved top-on area image, we want to do some regression and to generate offset, right? So this let star and the long star means the ground truth offset, and this let and long means the predicted offset. So we train this MLP layers to do this offset prediction. Okay, and so here we did some experiment on our collected vigor data set. So we did this same area evaluation and a cross area evaluation. So same area means same city specifically in our data set, right? So you have the data collected from the city of Chicago. You're using part of the Chicago data for training and using the rest of the Chicago data for testing. So cross area means you use the Chicago data for training, but you test on the maybe New York or Seattle data. Okay, so if you look at the result from the same area, if we're using all the loss functions we propose, right, using the normal triplet plus these IOU to consider the semi-positive, and also using the offset prediction, we are able to gradually improve the performance, both for same area and across area. Okay. One thing to note that is, the cross area perform much worse than the same area, which is understandable, right? Because, different cities, their building style or their scene layout are much different. So it's make the generalization performance much harder. Okay, so that's why you see much less retrieval accuracy. And we also did this in terms of meter level evaluation. Basically, we can set a couple of thresholds, right? So if the predict GPS and the difference between the predict GPS and the ground truth GPS is within a threshold, within a certain threshold, then we consider that's a correct prediction. For example, we can see at this 15-meter threshold, our method is able to outperform previous state-of-the-art by a large margin, over 15% of improvement in terms of accuracy. So that's for the same area evaluation. And this is also the same for the cross area evaluation in terms of meter level evaluation. We also evaluate the effect of this offset prediction, right? How accurate or is able to refine the final prediction accuracy. So we compare with retrieval only, which you only did the retrieval, you don't do the offset prediction. And our method, which is the red line regression method, is able to improve the performance, especially under this kind of low threshold setting. So another baseline we did is just classification. Basically, we take the reference image and divide them into like 100 cells, right? Divide them into a cell grid and make them like maybe 100-way or 200-way classification problem. Okay, again, this regression has much better performance as just simple classification. And this is just a visual example to show how this offset prediction is able to help geolocalization, right? So the green is the ground truth. So the blue one, diamond, is no offset prediction. And the red square is with our offset prediction. So clearly, we are able to make the final prediction closer to the ground truth. Another experiment we did is the noisy GPS refinement. As I mentioned before, in real-world application, for example, your cell phone GPS may not be very accurate, right, in terms of like millimeters. They may have some noise, especially in the crowded city, right? You have those tall buildings, 10 block signals make your GPS prediction or signal very noisy. But in this case, we can use image geolocalization to refine this noisy GPS, right? So let's say you have you have a noisy GPS, and so you can using that noisy GPS as the center, right? Instead of using the whole data reference database to do the search, you're using that noisy GPS as a center and take maybe 1,000 meters at the radius as the search radius to gather the area of image. So in this way, your search space is much reduced, right? Because you are using the noisy GPS as a reference, and just search the radius along that center. So as you can see that, with the search space become smaller, right, in terms of the radius, the accuracy is able to improve because you don't have much of the confusing examples in the retrieval process. Okay. So in summary, from this work, we propose a new benchmark for this cross-view image geolocalization beyond this one-to-one retrieval, which is a more realistic setting for real-world application. And our method is able to significantly improve the 10-meter level accuracy. And the data set as code is available on this link. Finally, I want to introduce our latest work that is using Vision Transformer for this cross-view image geolocalization task. And this is published in CVPAR PR 2022 this year. So as you have already seen a couple of examples, right? So cross-view image geolocalization is very challenging. It's because of this domain gap, right? The visual appearance very dissimilar. So the street view, you have some of the side of the buildings, road, but on the satellite view, you only see the roof of the buildings. So that's why some of the early work, they suffer from low performance. If you look at the top one retrieval accuracy, right, it's not very high, like 80%. So they suffer from this domain gap. Recently, there's some work utilize this polar transformation to mitigate this kind of domain gap, okay? And is able to significantly improve the retrieval performance, maybe by 10 or more percentage. So this polar transformation is able to work well on the CVUSA dataset. As I mentioned, this is spatially and orientation aligned dataset. And this dataset has images mostly focused on the rural area, okay? So for the polar transform is basically, take the aerial image, then do some transformation, which makes very close to the ground view appearance. Okay, so this is how they mitigate the domain gap for this cross-view geolocalization. But we did this for our Vigor dataset, which is not spatially aligned, and a lot of and as we collected on the major city of the U.S., right? So this is in the urban area, right? So a lot of tall buildings, and if we apply the same technique using the polar transform, and the performance is not able to be improved. As a matter of fact, the performance even getting worse, right? Using the polar transform on our data set, the performance even dropped by like 9%. And if you look at the transformed image, right, it doesn't make too much sense, right? So this is the street view image, but if you do the polar transform of the aerial reference, which has the top of the building, and you do the polar transformations, there's still a very large gap between the visual appearance of these two views. So in this case, how do we bridge this domain gap, right? So we try this polar transform with the CNN pipeline, it doesn't work well. And here in this paper, we propose to using the vision transformer, okay? So for the vision transformer, it's getting a lot of interest in the vision domain for various tasks. Basically, all the tasks people are exploring the vision transformer. It has a few nice properties. One is the vision transformer, because using the positional embedding, it is able to explicitly explore the positional information. And also it is able to model the global attention. Okay, so we want to leverage these two nice properties in this cross-view geolocalization task. And we propose the framework called TransGeo. Okay, so the setting is the same. So we still have the street view as a query, and we'll also have the area view image as the reference. So using the vision transformer, we first divide the images into small patches. Okay, as a common practice. Then for each of the patches, we do the feature embedding, okay? And we also add the position encoding, okay? So because we know the location of each patch, right? So we can add the positional embedding. And we can have two separate transformer encoder because they have very different visual appearance. So we have one street view transformer encoder to encode the feature. We also have another area view transformer encoder to encode the feature from the area view. And once we have the feature embedding, we're using the usual triple loss as the optimization function. So we consider this is the first stage of the transgeo pipeline. And at the second stage, we using the notion called attend and then zoom in, right? Just like human observe, like how we are able to find some useful information from the street view or the area view, so that we can see some of the clue they are a matched pair, right? So on the second stage, we generate the attention from the area view transformer encoder, right? So this is the attention map. And we're using this attention map and do some the non-uniform cropping or patch selection. Okay, basically we select the patch has the high attention value. Okay, and we are also using a higher resolution of the image. So this is because of the traditional setting, the average image is usually very large, like 1,000 by 1,000 pixels. So usually people do this work, they have to resize or downsize the area image to a smaller resolution to enable to fit the GPU memory, etc. So in this case, we using the attention to selectively search, select the most informative patches from the area view and using their original high resolution to hopefully, we are able to get, some of the information that has been lost during the downgrade or downsampling. Okay, so that's called the zoom in step. Okay. So with the select patch, we do this again, right? We go through this transformer encoder, and we can do this triplet loss function to do the matching. So this is like a two-stage process of the pipeline. So here, just basically show a detailed procedure of this kind of non-uniform cropping or patch selection, right? So from the attention map from the stage 1 transformer encoder of the area view, we can generate the attention map, and basically we can set a threshold, right? And generate a binary mask, okay? And then we use the original high resolution area image and select the corresponding high resolution patches and feed that into the second stage of feature encoding and matching. So we did some comparison on our Vigor dataset. So as compared to previous work, this transgeo approach is able to significantly improve the performance under all different evaluation metric, especially for this top 1 retrieval accuracy, about like 20% improvement over our previous work on Vigor. And we also did the meter level evaluation like we did in the Vigor paper. So again, the transgeo is able to outperform existing method at different thresholds. We also did the experiment on the CVUSA dataset, which the query is exactly located at the center of the reference area image. So our method is able to slightly better than the method using the polar transformer. So in our case, we do not using the polar transformation, just purely relying on the transformer framework. We are also the first to do some of the evaluation in terms of efficiency. So compared to the state-of-the-art method, our method is able to improve the retrieval accuracy, but also enjoy computation and memory efficiency, right, in terms of GFLOPS and the GPU memory. We also did some evaluation, under the unknown orientation, right, like we did in the first work. In the first work, we are rotating the area image. Another way is we can, shift the panorama image, right? So if the original orientation is located in the center, let's say this is maybe north, right? We can shift the panorama a certain, rows or columns, right? Shift to the left or shift to the right to destroy that alignment information. And under this unknown orientation, our method is again able to outperform the previous method, which is ours on bigger data set. Another experiment we did is the under the limited field of view, right? So for the vigor, we collect the panorama, which is a 360-degree view, so a full coverage of the scene. But for some cases, right, you maybe have some images collect from Flickr or Instagram, maybe only cover like a partial of the scene, right, 180-degree or maybe only 90-degree. With this kind of limited field of view evaluation, again, our method is able to outperform previous method. And here are some of the visual examples show the retrieval performance. So this red indicating this is the top one retrieved image, which is the corresponding to the ground truth. And the second example shows the ground truth actually rank second in our top retrieved image. And the third one is we consider a failure case because the ground truth is not in the top 5 retrieved image. But as a matter of fact, if you look at the top one retrieved image, this is considered like we retrieve the semi-positive, right? Because this is just shift a little bit, maybe to the left, right? So still cover some of the views of the ground truth location. And here's some other visualization example on another data set, CVSA. Okay, so in summary, for this work, we are able to propose a transformer-based method that is performed very well without polar transformation due to the explicit positional embedding property. And also by removing a large portion of the patches from area view, it does not cause performance drop, right? As a matter of fact, we can leverage this to using higher resolution patches to further improve the performance. And again, the code is also publicly available under this link. Finally, I want to conclude the talk by give a couple of future research directions. The first one is we can considering combine same view and cross view settings together, right? So right now in this field, the domain kind of divided in these two separate fields, right? So there's people working on same view geolocalization, but also folks working on purely cross view geolocalization. But in the real world application, both street view and area view exist in most cities, right? Like in large cities like New York, Chicago, you have the Google Street View cars, going around all the streets. So the street view image is also available, right? So we should definitely consider both, and they are also complementary to each other. So the same view has better performance, but do not have full coverage. But the cross view is easy to collect, right? Because we have the satellite is easily able to collect those satellite image. But because of the appearance gap, they have low accuracy. So we should consider, combine these two views together, right? Whenever that query location, if they have both street view as well as satellite view images, we can use them both to further improve the overall retrieval performance. And the second direction is we can consider not just focus on the image, right? We can also consider geolocalization using ground video, right? So now we have dash cameras constantly recording videos, right? Or autonomous driving vehicles that has all kinds of cameras to recording the videos. So we can using videos which contain rich information to do the geolocalization rather just using a single image. Okay, so in fact, we already have a work on this topic, ground view video-based geolocalization, which is published in ECCV 2022. And we also collect a new data set, which has ground GPS tagged videos as well as the corresponding satellite images. So the data set will be publicly available. So if you're interested in this topic, you can check out paper and maybe play with the data set. Okay. So here are some of the key reference I mentioned in the paper. mostly published by my PhD student. With that, thank you for your attention. And if you have any questions, I'm free to answer. Yeah, thank you.